It was good.
What did you do over the weekend?
What we're looking at today is special types of factoring, a special type of factoring, and it's difference of perfect squares. Now there's other two types, and one of them is the sum of squares. And difference of squares. No, these two here will show up, and we'll see these types. But I feel it takes longer to try to work out the special properties that give us these two formulas than it would be just to use the steps we had last week. So our main steps for solving these, factoring out a greatest common factor, our two sets of parentheses, finding signs, factors. It's going to be easier to do, especially with these two here, to do it the way that we've solved for chapter 3.1 than it is to figure out and learn the special methods for these here. Now the difference of perfect squares, or the difference of two squares, this method is actually a lot easier to do, and it works out nicely. Now it's not going to say, I'm not saying that the steps we did last week don't work, because they do. If we notice there are a difference of perfect squares, so the first term is a perfect square and the second term is a perfect square, it will work out like this here. We'll get that a squared minus b squared is equal to a plus b times a minus b. And it'll work out this way every single time. Now the main thing we need to look at and see when we look at a difference of perfect squares, we need to determine, is the first term a perfect square and is the second term a perfect square, and are they being subtracted? So if we have a difference of perfect squares, there's not a term with just x. There's not a term with just x to the first power. So we look at this here. So we just have x squared and we have 25. We don't have a middle term. There are two terms being subtracted. So this is very similar to our a squared minus b squared. We just need to determine, is x squared and 25, are they both perfect squares? Now the way we can determine if they're perfect squares is seeing if we can take the square root of them. Well, the square root of x squared would be x. The square root of 25 would be 5. Because the square root of 25 is 5. 5 times 5 gives us 25. So what that tells me is that the first term, x squared, is a perfect square. It tells me 25 is a perfect square. So really what we can say with this here is that we have a, which is our x squared. Our b is our 5 squared, because if we simplify these out and actually square them, we'd get back to the original equation. And what we know about this here, a squared minus b squared, that's the same. One factors, it factors to a plus b times a minus b. Because when those factor out, they factor this here. So looking at this problem here, our value of a is x. So in here and here, we plug in x. Our b value is 5. So in both of spaces, we plug in 5. Because this is really going to revolve around the fact that a squared minus b squared is equal to a plus b times a minus b. If it was asking us to solve it, yes. But here it's just asking us to factor them. Mm-hmm. Yes, we're mainly just sticking to the backwards distributive property. We'll see these here, how to solve them tomorrow and Thursday, or tomorrow and Wednesday. We'll spend 2 days kind of solving them and going over some different methods beyond factor to solve them. Any questions on this here before we look at another one? Yes. Mm-hmm. Well, I wrote it that way just so we can kind of distribute and connect the fact that a and b, that x is a, so x is also going to go in here and here. 5 is b, so it goes here and here. So we don't necessarily need that step, this step here, because we could go and see, okay, this is a, this is b, plug them in, plug them in. And that's especially once you get used to doing this here, the difference of perfect squares and seeing where they connect. This here is a little bit faster than doing our normal, the factoring we did last week, yes? Because if we can see it's a difference of perfect squares, it works a little bit faster. Yes. No, we're good.
The bottom part, that is your answer, right?
Yep.
That's the bottom. So you put the x squared minus 5 squared equals, and then that whole.
So that works. I mean, we could have that. Because, I mean, it could have it saying that x squared minus 25 is equal to our x minus 5 times x plus 5. It factored is this here, or the expression factored is x minus 5 times x plus 5. Any of those. Those are saying the same thing. Now let's look at another example of this here. So we have 4z squared minus 1. So we do have two things being subtracted, and we need to determine, are they perfect squares? Now the main way that we can determine if this is a perfect square is by taking the square root of 4z squared and the square root of 1. Now we can't type the square root of 4z squared in the calculator because the calculator needs a value for z, but we can type the square root of 4. And the square root of 4 would be 2. The square root of z squared is z. So the calculator won't do the square root of 4z, but it would do the square root of 4. And then we can do the square root of z by itself. Now what's the square root of 1? 1. So is 4z squared and 1, are they both perfect squares? Well, yes, square root of 4z is 2z, and the square root of 1 is 1. So that tells me I do have a perfect square, a squared minus b squared, which simplifies to what? A plus b times a minus b. So looking at this here, what is the value of a? What would be the value of a? It would be 2z. So in both of our spots, we'd put 2z and 2z. Now what's the value of b? And we're done. We factor this here. So one of the big things that we need to notice about the difference of perfect squares is that really our terms in the first spot and in both of these spots here where a and b go are going to be the same. Both of these sets of parentheses are going to look almost identical, except the signs are going to be opposite. Both of our terms, so the terms for a and b are going to be the same. We're just going to have an opposite sign in the middle. And that's going to work on all these. Any questions on this here? Let's look at this one here. So we need to factor x squared minus 64. So I want to see, is this a difference of perfect squares? Well, to check it, I need to take the square root of the first term and the square root of the second term, the other term. Because if I can take the square root of both of these, then these are perfect squares. So what would be the square root of x squared? Square root of 64. Hey, and we can plug 64, we can plug numbers into the calculator. We can't do variables. But if there's a number in front of the variable, we can plug the number into the calculator. We just can't do the variable. So what this tells me is taking the square root of x squared tells me that the first term is a perfect square. Taking the square root of 64 tells me it's a perfect square. And since they're being subtracted, and there's only two of them, this is a difference of perfect squares. And our form for difference of perfect squares is a plus b times a minus b. So looking at this here, what's the value of a? The value of a would be what? X. So in both spots where there's an a, we would put x and x. How about b? We'd have 8 and 8. And that's it. That's all we have to do for this here. Questions on these here? We good with this here so far? I want you, let's see here. Let's look at this one here. So we'll skip x squared minus 36 because that one's not too bad. But let's look at this one here. Now this one here doesn't have a variable in front, but we do have two numbers, yes? So let's see if they are perfect squares. Can we take the square root of 100? What times itself is 100? 10. Square root of m squared would be m. So are both of these perfect squares? Yeah. So we don't have to worry too much about making the variable positive here. It'll still work out. Because this does fall in line with a squared minus b squared. We'd have our a plus b times a minus b. Now looking at this here, what is the value of a? What would be the value of a? 10. Because it goes, the 100 goes in the first spot, that's where a is. So I'd have 10 and 10. What's the value of b? M. So we'd have m and m. And that's it factored. Any questions on this here? That's all we have to do for this here. And that's the answer. Any questions on anything we've done so far? Now this one here looks a little bit harder, yes? Because we have 9n squared and 16, or 9n squared minus 16. But we still have two things being subtracted, and we don't have a middle term, correct? So let's see if it's a difference of perfect squares. So I need to take the square root of 9n squared and the square root of 16. What's the square root of 9? Square root of n squared would be square root of 16. So this here is a difference of perfect squares, yes? I mean, most all of these are. That's what we're looking at. So this follows our a squared minus b squared, which is a plus b times a minus b. Well, what's the value of a? 3n. So in both of our first two spots, we'll put 3n. What's our value of b? 4 and 4. And we are done. Questions on these here? I want to look at this one here. Okay. This one here is not on the note sheet. I know that I intentionally picked this one in particular. There's not going to be one like this here on the homework, but there might be something like it, especially on the test when we're trying to solve. So the first thing we need to look at to see if this is a difference of perfect squares, and it is to see if I can take the square root of 50x squared and the square root of 72y squared. What is the square root of 50x squared? Well, I know the square root of x squared would be x, yes? What's the square root of 50? If you're having trouble doing it in your head, you can always use a calculator to see what the square root of 50 is. 7.5, or as a radical, it would be 5 square root of 2. And 36 or 72 would be 6 square root of 2, especially if we use the yellow calculators, it'll tell us that. So it's 50 and 72, are they perfect squares? No. Is there a greatest common factor between these two? 2 would work with both of them for sure, yes? So let's factor it out and see what happens. If I factor 2 out of 50, I get, is 25 a perfect square?
Yes.
5 times 5, yes? 72 divided by 2 would be? Okay, so there are perfect squares, yes? Sometimes there's a greatest common factor between them that we have to factor out. Sometimes there's a greatest common factor that we need to factor out. Because now if we check it again, 25x squared, if we take the square root of it, we get 5x. 6y. So it works. So because of that greatest common factor of 2, that's what messed it up. So what would be the value of a, the number that goes in the first spots? It would be the 5x, because 25x was first. Its square root would go first. So we'd have 5x and 5x. Our value of b would be 6y, so it would go second. Any questions on this here? Any questions on anything we've done so far? Okay. Let's look at the last thing we're going to do today. Evaluate a numerical expression, these here. So trying to do 54 squared minus 48 squared, that seems a little challenging, yes? But doesn't this look very similar to our a squared minus b squared? Well, yeah, so what I could do is I could break it up, because this would be 54 plus 48 times 54 minus 48, yes? Because it's our a squared minus b squared. Because a squared minus b squared did factor to a plus b times a minus b. So our value of a was 54, the value of b is 48, so we could rewrite it like this here. Well, 54 plus 48 would be 102. And 54 minus 48 would be 6. At this point here, we can multiply them together, carry the 1. And we'd see the 54 squared minus 48 squared would give us 612. Does anybody see an easier way to solve this than doing this step here? There is one. There's a real easy way. Yeah, there's no reason that you can't just type this straight into the calculator. There's just numbers. So with any of these here, like with this one here, you could type 68 squared minus 62 squared straight into the calculator, and it would tell you what the answer was. It actually give you the answer. The way that doing this here with our a minus, or a plus b times a minus b, or for this problem here, which would be 68 plus 62 times 68 minus 62. Doing it this way is if you weren't allowed to have a calculator or you didn't have one to solve this. Because it'd just be 130 times 6 which would give us what, 780. So there's nothing wrong with typing these here into the calculator. The calculator will tell you exactly what it is. And it's a lot easier than doing it that way. So here, use a special product. No, just plug these in the calculator and you'll get the answer. Any questions on anything we've done so far?